Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day, here in my virtual classroom. Step on inside as we jump into section 5.4 in the Big Ideas Math Integrated Math 1 textbook. This is on solving special systems of equations. Now, as is generally the case, I don't look ahead to see what comes up, and as I did sections 5.1 to 5.3, I've mentioned special cases, and I said, you know what, it's interesting that they haven't arisen yet. Well, because they devoted a whole section to it. Now, I'm back and forth on whether or not they should have done it. I understand, I guess, why they may. But if we live in a vacuum with these things and everything's a special case, it'll be kind of interesting to me. And just as I just said, as I don't look ahead, I don't know if they do that for all 32 problems that they have, if all of them are special cases or not. But if they live in a vacuum with this stuff, please understand as we do reviews of things that we have to understand when special cases arise and when they don't, and how to do one solution things, stuff like that. So we will probably solve using all the methods that we did before, which is one cool aspect of this. We can use graphing, substitution, and elimination. Maybe they force some on us so we get some of the review within, but all with special cases involved. Special cases to us means, you know, infinite number of solutions, no solution, things like that. We'll see what it looks like graphically as well as in the algebraic equations. If you'd like to jump to the description section down below, you can download the PDF of this textbook section, and also probably graph paper if we're going to solve some things by graphing, and then also find the timestamps of the problem sets as I begin with the lecture portion first off. Without further ado, let's go ahead and get started. We're going to determine the number of solutions of linear systems and use linear systems to solve real-life problems, word problems here again. I'm curious as to how the no solution or infinite number of solutions cases work for the special cases on these. Previous phrase is parallel, and something that we actually did within chapter, I think it was chapter 4 that we started first talking about parallel lines. So numbers of solutions, we've all seen one solution cases, and that's what they first say. A system of linear solutions can have one solution when just two lines intersect. They intersect once. That one point, that xy that we kept finding every time as an ordered pair that is the only x and y that's a solution for both equations in the system simultaneously. No other point is a solution for both equations. You can have no solution. Graphically, if the lines are parallel, that means they never intersect. No point of intersection means there's no single xy that works for both equations simultaneously. But infinitely many solutions pretend like there's one line on top of the other. They say the lines are the same. There's a blue line, and right above it is this green line right here, right? Infinitely many solutions. It doesn't mean all real numbers, right? You can't plug in any x, any y on the graphing plane, just only the x's and y's that are on the line, but it's still infinitely many. Not just one, and obviously not zero. First example with a no solution case, what it looks like. They says solve by graphing this y equals 2x plus 1, y equals 2x minus 5. Now, maybe from the onset, you can actually tell these are going to be parallel. They're both slope-intercept form. 2 is the slope of this, 2 is the slope of that. Same slope. Different y-intercepts means you start from this negative 5, rise 2, run 1, etc., draw the line, and start from 1, rise 2, run 1, etc., and you draw this line. These lines will never intersect. Because they don't intersect, there's no point that's a solution to that is the solution of both equations, so the system has no solution. Now, before I move forward to solving algebraically using, say, substitution, I want to bring up something that I did bring up in some of the other videos, was that's why it's important that if you make a graph, like, let's say you were solving by graphing. I think I must have talked about this in section 5.1. Let's say you're solving by graphing, and you mess up your graph stuff. And I'm not talking about this kind of problem. I'm talking about a normal problem where two things would have intersected here and here, boom, like that, right? So in a case like that, and I have to respond to a message after this, in a case like that, if you do a graph thing and you accidentally graph something wrong, and then boom, this line is like this and this line's like that, and you can't see them intersect in the window range, this one and this one right here, then you probably graphed wrong, and you can tell because you should be able to see them within your window range and they should intersect. Just because they don't intersect in your window range doesn't mean no solution. Clearly this line will intersect with this line eventually up here and they'd have a solution. But if you can't see it, then that's probably not how we solve by graphing. You probably graphed wrong in that scenario, or we have to change the scaling obviously. So I just wanted to bring that up. These ones are clearly, truly parallel. They'll never intersect no matter how long the lines intersect. Let me respond to a message. Give me a second here. Okay, method number 2 is solving by substitution. Now, we could also look to elimination, things like that, but this is clearly set up for substitution. Y is by itself. So you set 2x plus 1, you substitute it for y, or 2x minus 5 for y, or however you call it. You plug it in, you have 2x minus 5 equals 2x plus 1. When you subtract 2x from both sides, you'll notice that you just get negative 5 equals 1. Now, we've seen this kind of situation before. variables cancel, left side doesn't equal right side. That is a classic no solution case. So we've seen these. We've also seen the infinitely many solutions. We'll jump into that. This is also known as an inconsistent system. No solution when variables cancel and left side doesn't equal right side. This would also be true if we did this for elimination method. Variables would cancel, left side wouldn't equal right side. Let's look at an infinitely many solutions case now with this. Let's look at it as a graph, and let's look at it as a solving algebraically. We have two equations written in standard form. Their version of graphing, they I don't know if they rewrote them in slope-intercept form, what have you. Doesn't really look like they did anything specific. But what I would do in this case is I would rewrite this top equation in slope-intercept form. Y equals, 2x plus 3, adding the 2x to both sides. Over here, see if I add 4x to both sides and then divide everything by 2, you also get y equals 2x plus 3 here. Let me clear my throat. Hang on. Full of problems in the lecture portion, I am. Now, you can tell they're actually the same equation. Now, at that point, do you need to graph? I don't know. Maybe, sure, whatever. But, in disguise, right now, you can't actually tell that they are the same equation. Maybe you can. Maybe you know what's up with it. But when you get them in slope-intercept form, they're literally the same line. Same slope, same y-intercept. So, as you graph it, one line on top of the other, infinitely many solutions, basically. Infinitely many solutions in this case, where every solution for one is a solution for the other. You don't list them because they're infinitely many. Solving algebraically, they show the elimination method. If you multiply the top equation, say, by -2. I personally would have divided the bottom equation by -2, but that's okay. If you multiply the top equation by -2, you can see that things cancel. I mean, everything cancels. 4x minus 4x is 0. -2y plus 2y is 0. -6 plus 6 is 0. You get 0 equals 0 as a statement. It's just variables cancel, left side equals right side. This is a classic infinitely many solutions case that we've seen before. And elimination probably made more sense for this problem as it was originally set up. So infinitely many solutions for a case like this. That is known as a consistent dependent system. Dependent system. Okay, an independent, well, I don't know if they showed it, but one solution would be consistent and independent. A consistent independent system. Whereas no solutions was an inconsistent system. Solving real-life problems, modeling with mathematics. I'm really curious to see if any of these have infinitely many solutions or no solution. I don't know what they're going to say on these ones. The perimeter of the trapezoidal piece of land is 48 kilometers. Perimeter. Add these up, you get 48. Boom, 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 boom. So you can see that set up right here. The perimeter of the rectangular piece of land is 144 kilometers. Boom, plus boom, plus boom, plus boom. Is 144. You can see that right here. And simplified it and simplified. Write and solve a system of linear equations to find the values of x and y. So given that they are the same x and y that represent both, they can be in the same system together. So right here and right here. It says, wait, what does it say? Write and solve a system of linear equations. So interesting. Because what I'm noticing here is, I mean, they're using method 1, solve by graphing. If you do some rewrites of these equations, heck, if you these might be able to have intercepts that are integer values. The x-intercept here is 8, the y-intercept here is 4, and I suppose here the x-intercept is 8 and the y-intercept is 4, because these apparently are the same line. When you draw them, they are the same line. That means that has infinitely many solutions, which is where they say right here. But that doesn't mean that we can't write out an x, y value that still works. So I'm interested to see what they say on that. Now, algebraically, you can solve using elimination. So I wonder if we have a choice on which to use, or if they're going to say choose both methods. But right here, if you multiply the top equation by -3, again, I could have divided the bottom equation by -3. Then everything eliminates. 0 equals 0, infinitely many solutions. Now, it says the solutions are all the points on the line in quadrant 1. So it has infinitely many solutions. So that was just their answer, but you want to do quadrant 1 only. And the reason for that is because we can't plug in an x value or y value of 0 or negative, because that would lead to 0 or negative lengths, and you can't have those. Only positive lengths. They said write and solve a system, so it is infinitely many solutions on that line. That means, for example, this point, assuming that's 2, 3, 2, 3 is a solution to the system. You can plug in 2 for x and 3 for y, and it'll work. You can plug in 4 for x and 2 for y, it'll work. You can plug in 6 for x and 1 for y, it'll work. Can't plug in the zeros. You can plug in some half values. Anything that's on the line works. There's an infinite set within there. There's a real world problem with that. All right, that's the lecture portion itself. So I wonder if all the word problems will do that. I wonder if all these are special cases. I have no idea, but we'll go ahead and get started. Vocabulary and core concept check number 1. Is it possible for a system of linear equations to have exactly 2 solutions? Explain. System of linear equations, 2 solutions, no more, no less? No. No. They can either intersect once, not at all, or infinitely many times. Lines can't curve back, can't angle back, whatever you want to say. I'll say curve back. See, they said linear ones. So if I had, for example, see, lines, they can either intersect once, whatever, but if this was a curve, a parabola, for example, okay, now it can intersect twice. That's not linear, though. It can have infinitely many solutions, but that's more than 2. So no. Number 2, compare the graph of a system of linear equations that has infinitely many solutions and the graph of a system of linear equations that has no solution. Infinitely many solutions has, when you look at the equations in slope-intercept form, it's the same slope and same y-intercept. They're literally the same line. Infinitely many solutions equals same line, one on top of the other, if you will. No solution is parallel lines. That means they don't ever intersect. These intersect always, these intersect never. And that's the difference between those two. That's all I'm really going to say on those ones. Before we go ahead and get started here, I believe it's numbers 3 through 32. So I'm going to go ahead and get started with you guys. And like I said, these problems might live in a vacuum, meaning we expect no solution. We expect infinitely many solutions. Great. But we have to be aware of being able to use them whenever they surface at any time. But what we get to do is choose multiple methods, it looks like. So we'll see what they do. In exercises 3 through 8, match the system of linear equations with its graph, then determine whether the system has one solution, no solution, or infinitely many solutions. So this is kind of solving by graphing, but without us needing to draw the graphs themselves. So on number 3, we have negative x plus y equals 1 and x minus y equals 1. If I were to use the standard form approach of this, this would have an x-intercept of negative 1 and a y-intercept of positive 1. And this one here would have an x-intercept of positive 1 and a y-intercept of negative 1. So probably slopes of 1 and negative 1 as well. Let's see. That's not going to be A or B or C or D. It might be F, actually. This one, there's one of them that has a y-intercept of 1, right here, a y-intercept of 1, an x-intercept of negative 1, and this one here has an x-intercept of 1 and a y-intercept of negative 1. So that's those ones. This belongs to graph F, which has no solution. It is an inconsistent system, my friend. You get an F, sir. You get an F. Let me cross that one out. Now, I didn't do any extra work on this, but I very well could have. If I added down these lists, that would be more of an algebraic approach. If I added down these lists, I'd get 0 equals 2. 0 equals 2 is also an inconsistent set with no solution. Number 4. And I'm going to try and not do it algebraically, right? I want to serve these for solving by graphing as long as they are these kinds of questions. Later, we're clearly going to do a lot of algebraic problems. 2x minus 2y equals 4, and negative x plus y equals negative 2. In this case here, once again, if it's in standard form and I can get intercepts out, I'll go ahead and do that. An x-intercept, if you divide the x's and constant by 2, you get x-intercept of 2. Y-intercept is negative 2. So there's one graph. Let's find this one where you get an x-intercept divided by negative 1, you get 2. And the y-intercept, you get negative 2. So, hey, you get the same 2 and negative 2 out. That means they'll be the same line. I mean, literally, 2 points make a distinct line. And so these are the same line. But we have to find the ones with the 2 and negative 2. It must be this one right here on E. 2 and negative 2 for x-intercept, y-intercept. And, of course, if it was green as well. So it looks like we're going backwards, folks. The next answer should be D, shouldn't it? This is E. This is infinitely many solutions. Infinitely many solutions. Any points on that line represents solutions to both equations in the system. So starting us off the bat there. And I say starting us off the bat because it looks like 2 of them will have one solution. I guess not everything's a special case, so they can differentiate some. Number 5. Number 5, we have 2x plus y equals 4. Negative 4x minus 2y equals negative 8. Once again, we live in a set where I can determine x and y-intercepts by dividing by coefficient value by the constant over there. So my x-intercept will be 2. My y-intercept will be 4. And on this one in green, if I divide by negative 4 here, I get an x-intercept of 2. It looks like here I get a y-intercept of 4 when I divide by negative 2 here. So same line once again, but x-intercept 2, y-intercept of 4. Looks like it's not D. Looks like it's B right here. Boom. Y-intercept 4, x-intercept 2. This is going to be B. Let's cross out E because we already took care of that one. So this will be B, B, B. It is infinitely many solutions since it's the same line. I might say, Mr. Robinson, why aren't you doing slope-intercept form? Well, I can do what I want, right? Slope-intercept form or standard form. I'm out of standard form right now, and if I can get intercepts out of them that are very clean numbers, I'm going to continue doing that. I'll use slope-intercept form if the numbers are not clean by dividing. Case in point, I look at this bottom equation right here. I'm going to rewrite that in slope-intercept form. So you can see it here. Number 6. I have x minus y equals 0. I would actually like to also rewrite this in slope-intercept form. And the reason why is because an x-intercept and y-intercept of 0, 1 point does not a line make, right? If I told you the x-intercept and y-intercept are 0 right here and said draw the unique line through it, there's not one unique line that goes through this. It can be any line right here. And if I rotate it, right, it can be any line that's on that point. Any of these have the same x and y-intercept of 0. So that's no good. We're not going to do that. So I'm going to rewrite both of these in slope-intercept form. This one, if I add y to both sides, it'll say x equals y. But in other words, I could also rewrite that as y equals x. That means y equals 1x plus 0. Keep that in mind. That's a unique line for this. And for the other equation, we have 5x minus 2y equals 6. Let's get this y by itself, first by subtracting 5x from both sides. And then dividing everything by negative 2. So 5 halves x minus 3, like that. So these are the two lines we're looking for, right? Slope. Now, they have different slopes. So these will be, unique lines, and they are not parallel. Which one has the 1x plus 0? Looks like it's in C, right here. This 1x plus 0 is this guy. And this one must be 5 halves x minus 3, a y-intercept of negative 3. And up 5 over 2. Yes, it looks like that one. Now, there's only one specific solution on it at that point, 2, 2. They're just asking how many solutions are there. This is one solution. This is this is graph C, system C. And one solution. Now, when you have one solution, guys, we will identify them in conventional problems. This one is just asking you to identify how many. But otherwise, we don't just say 1. We would say, 2, 2. All right, number 7. It's either A or D. Number 7. We have negative 2x plus 4y equals 1 and 3x minus 6y equals 9. Your wish is granted. If you wanted more slope-intercept form, you got it. I can't divide 1 by both 2 and 4. 9 can divide by 3, but not by 6. So I'm going to go for slope-intercept form on both of these. We have 4y equals 2x plus 1. Divide by 4, 2/4 reduces to 1/2, and here's a 1/4 right there. Still a fraction y-intercept. I'm not a fan of that, but we'll still be able to identify which one has that y-intercept fraction as we rise 1, run 2. This one right here, we can subtract 3x from both sides and divide by negative 6, and I think we have the same issue here. There's a 1/2 x here, and then divide by negative 6. That's minus 3/2 when you reduce that. So here's the nice thing about it, though. We can tell these, same slope, different y-intercepts. They'll be parallel. Looks like it will be option D. Let's see if they actually cross where we expected them to cross. The blue one crosses at a y-intercept of 1/4. That must be this here. Negative 3/2 is also negative 1/2. So negative 1/2 looks like this. And we have some sort of rise 1 over 2, up 1 over 2, and same thing like that. So this looks to be D. Itchy nose D. So option D. They never intersect. They are parallel. You can tell by the equations as well. These are no solution. Now, as much as, we are going to be solving some of these algebraically. Maybe we have to draw our own graphs later. I don't know. But as far as these go, even if you see these and right off the bat, you could tell yourself no solution. If they say solve by graphing, we got to draw the graph. If they say solve by elimination, keep proceeding onward until those variables cancel. I get it. You made your own conclusion, and later in life, maybe you can actually state those and keep it that way. For the sake of the exercises right now, we'll proceed as needed. So number 8 must be A, but let's go ahead and confirm all that with what we got with more slope-intercept form. Because I will get fraction x, y-intercepts that I would otherwise not prefer to look at out of standard form. So with this one, subtract 5x from both sides and divide by 3. Negative 5/3 x plus 17/3. Still not the biggest fan, right? Still get fractions, but we can still play with it. The slope's the same, things like that. Subtract x from both sides. Divide both sides by negative 3. Negative x over negative 3 is positive 1/3, and negative 2 over negative 3 is positive 2/3. So these are the two equations, clearly different slopes. The negative 5/3 x plus 17/3. 17/3 is 5 2/3, so that must be this guy right here, as we're going down 5 over 3, down 1, 2, 3, 4, 5 over 1, 2, 3. Boom! We hit another point right there, like that. This one, 1/3 x plus 2/3. 2/3 is right there. Boom. And up 1 over 1, 2, 3. Boom! And that probably doesn't hit that point. Boom, right here. But that ends up being that line. Now, where they intersect, I have no idea. I'd probably have to use a different method for that. But there's only one solution there. So this is option A. This is option A. You can tell with the different slopes already, but one solution. So there's the beginning. And, you know, I linked in my previous video, I think in my section 5.3 video, I linked because they started talking about which method to choose to solve for and why. And sometimes you can solve by graphing. And, you know, some people don't necessarily love solving by graphing versus the algebraic methods you learned. I get it. Solving by graphing, though, seeing these graphs is kind of getting us an idea of what it means to be no solution or infinitely many solutions. So I like that concept, whether or not you like the graphing itself. Now, 9 through 16, they say solve the system of linear equations. They do not require a method out of us. They don't say use substitution, use elimination, use graphing. So it looks like it's up to us. We can make our own choice. I'm going to make this singular choice on each problem. I'm sure at some point I'm going to go ahead and say, oh, look, I'm going to use all three methods. We'll see. We'll see. But we just looked at a bunch of graphs, so I'm going to try and do algebraic as often as I can, unless graphing kind of flies in the face of like we should graph it, you know? So these ones have y by themselves here. That means I can do a, you know, classic case substitution. 2x minus 4 can take y's place up here. So I'm going to use substitution method. 2x minus 4 equals negative 2x minus 4. And I add 2x to both sides like that, and I add 4 to both sides, I get 4x equals 0. That's not a no solution case. Divide by 4, you get x equals 0. That's actually the x value. We still need the y value. Plug it into either equation. It should be the same. Y equals 2 times 0 minus 4, and 0 minus 4 is negative 4. So hey, there is one solution, and it is 0, negative 4. You know, I didn't know whether to expect to get that or not. I expect more special cases to be had. You should expect it as well, but that was a one solution case of this. And look, looking at the equations initially from the onset, they are different slopes, so it makes sense that it's one solution, right? They should be there. Now, on a lot of these other ones here, you know, again, when you look at them, you might know what to say, specifically on number 10. Number 10, they are in slope-intercept form, not that I'm going to graph them, but in slope-intercept form, we can tell they have the same slope. They have different y-intercepts. These are parallel lines. They will not intersect. I already know this will be no solution. But let's kind of reveal that in full. Again, do a substitution up here. We have negative 6x plus 8 equals negative 6x minus 8. Not much to say here, but negative 6x and negative 6x will cancel when you add 6x to both sides, and you get 8 equals negative 8. Now that's an indicator right there that that's not a true statement, and variables canceled, so we have no solution. Was it many steps to get there? No, and could have I realize that then and there? Yes. And we're going to continue to do that algebraically. That's why I said these problems lived in a vacuum are kind of weird, because not only do we expect these answers to happen, but when they do happen so many times, it's kind of like, well, these problems are kind of weird to do. It's only when they surface as you're doing other kinds of problems where you do have one solution, and you do 12 of them with one solution, suddenly one pops up with no solution. It's a little bizarro as it shows up, but you still deal with it. Like this one right here. Everything is opposite signs, and when I love to do elimination method here, and I will. So normally on elimination method, I say, when you add down the list, will something eliminate? The answer is not only yes, it's a resounding yes. Everything will eliminate. So this becomes 0, this becomes 0, so that means there's 0 on this side, and 6 minus 6 is 0. We get left side equaling right side. That's a classic case of infinitely many solutions. And that's our conclusion. That's all I need to say on it. That also means, by the way, guys, these are the same line. They might not be represented to look exactly the same. They're close, opposite signs. And that's how they tend to disguise them. You're probably used to that from chapters 1 and 2 when we had to do distribution and stuff to find out, oh, look, yeah, look, they're the same equation. So they try and hide them a little bit. This one, kind of the same thing. I mean, are they really hiding it? Not so much. We'll see what happens on numbers 13 to 16. But what's going to happen here? X's eliminate. Y's eliminate. You have 0. Do the 7s eliminate? Not so fast. You don't subtract these 7s. They do add. You get 14. 0 equals 14 is a no solution case. You know, this section might go pretty fast. I don't know. I actually spent slow time on the beginning problems, but yeah, it's a no solution case. But yeah, a lot of special cases, right? We're going to see a lot of those. Number 13. I'd love to do some form of probably elimination. They're in standard form right now, and I can see that things can line up in a certain way. But here's the thing. They did a lot of multiplication, right? Maybe they multiply this set by 2. I can divide this by 2 as well. You know what I mean? Divide these by 2, and you get positive 2x plus 2y. Make them smaller equals negative 4. It's whatever. It's up to you. Bottom line is everything's going to cancel. Boom, boom, boom. When I say cancel, I mean equals 0. So 0 equals 0, infinitely many solutions. I'm shocked. I'm surprised that this was a thing that occurred in this section, right? Infinitely many solutions. There was no possible way that this was going to be one of 2 outcomes. I guess 3 outcomes, but how often is one solution going to appear? Watch number 14, one solution appears. On number 14, you know, I'm going to fall in that same boat that I keep bringing up. If I can divide, I'm going to divide, or at least if it helps me, and it will here. So here, I can divide the top equation all by 5, and here I'll get 3x minus 1y equals negative 4. And take a look at that. When these things combine, that second equation with the newly written first equation, negative 3x plus 3x is 0. Y minus y is 0. 4 minus 4 is 0. 0 equals 0. We once again have infinitely many solutions. Now, I'm showing you that division step, meaning you can do it when you prefer to make numbers smaller instead of bigger. Do they help you in these problems? I don't know. At that point, they cancel. It's up to you. If you want to multiply, go ahead. But I like to divide whenever I have that opportunity to remind you that it's there. This is actually maybe a good opportunity to do exactly that. Let me show you what I mean. Number 15, assuming things cancel, I have no idea. We got to eliminate one variable. So this is one of those ones, okay, let's say we weren't in the vacuum of special cases, and you couldn't tell off the bat that this would be a special case, because it's likely that it is. It kind of looks like it is for reasons. You ask yourself right now, if you added down the list, would a variable eliminate? And obviously you say no, right? Nothing eliminates. So which variable would you like to eliminate? That's kind of a your choice thing. Maybe you look at the x's, they're smaller numbers, they're positive, things like that. So okay, we eliminate x's. Now, 6 and 9 have a least common multiple of 18. So you can multiply this by 2 and this by, say, negative 3 and change that. But we could also divide as well. 9 and 6 also have a greatest common factor of 3, and we can divide these by 3 and these by 2, and we can reduce it down. If you ever so have that preference, go for it. I can divide all these by 3, and then I'll get 3x minus 5y equals 8, and I can divide all these by 2, because this is where I go with it. Divide by negative 2, rather, as they can all divide by that, and these will be additive inverses there, and these can divide by 2 as well. Negative 10y divided by negative 2 is positive 5y. Negative 16 divided by negative 2 is positive 8. But take a look at what happened. Even although you had your intention to just eliminate x's, the unintended consequence was the y's eliminated. I mean, that's not a consequence, it's just the problem. 8 plus 8 is not 0, right? It's 16. So 0 equals 16, that's, it's not true. Doesn't mean you did anything wrong. On the contrary, you did everything right, and I shrunk the numbers as a result. This is a no solution case. But what I wanted to talk on strategy there is, if you can divide to get your things and make them smaller, not just for special cases, but even regular cases, I mean, you go for it. I prefer it personally. Number 16 doesn't scream special case to me. This looks like a one solution case, and now we're going to have to do what we need to for it. Now, elimination or substitution or graphing, I prefer elimination here. I think everyone here would. So there's only a couple substitution problems to begin with here. Listen, I'm going to eliminate the y's. They're already opposite signs, and actually they have a smaller least common multiple. than 3 and 4 do. So I'm going to actually eliminate y. So I'm going to multiply the top equation by 5 and the bottom equation by 2, straight up. The positive versions of those, because they're already opposite signs. So here we'll get 15x minus 10y equals negative 25. And here we'll get 8x plus 10y equals 94. Yeah, I couldn't divide there and do a reduction version of that. So the y's eliminate as we get 23x equals 69. Yep, and you divide by 23, you get x equals 3. So it's a one solution case. We're not done, obviously, and we need to do a substitution here. Let's do in that second equation. We have 4 times 3 plus 5y equals 47, or 12. And then subtract 12 from both sides, 35, and you get y equals 7. We divide by 5. So 3 comma 7. I'm not going to double check it. That sounds good. But one solution, you don't have to say one solution. You just got to say what the one solution is. And there it is. Yeah, I'm, next after this comes the chapter quiz. By the way, we're halfway done with this section. But next comes the chapter quiz. And although, yes, they do identify what section they are in, it'll be nice to get a good mix of all the different methods to do. But it's not until the chapter test, not even the chapter review, it's not until the chapter test that you get a true, they don't tell you which one it is, they mix the problems all up. It's only then that I feel that we'll truly get this whole, maybe special cases will pop up and prepare yourselves for them, but until then you gotta keep it. All right, in exercises 17 to 22, use only the slopes and y-intercepts of the graphs to determine whether they do. Okay, awesome. This time we don't have to go further into it, but they said use slopes and y-intercepts. That means get your equations in slope-intercept form. That means less work required for us, and maybe ultimately this is what you can do for the majority of your problems if you want to choose to do that. So on this first set here, I get y equals 7x plus 13. You can see the slope and y-intercept for that one. This one here, we're going to have to do more work. Negative 21x plus 3y equals 39. So let's see how it compares to this one. We got a slope here of 7. A y-intercept of 13. I probably won't write that each time. I just want to make sure you know what we're comparing. If I add 21x to both sides and then divide everything by 3, we get y equals 7x plus 13. That means we got here a slope of 7 and a y-intercept of 13. So same. Okay, they say explain. I mean, that's my explanation here. Normally I'll do it out loud. They are literally the same line. Same slope, same y-intercept. Same slope doesn't mean parallel if they're the same y-intercept. Now it means same line. Same line means infinitely many solutions. So I hope it's okay that for the most part, guys, I'm going to be vocalizing why these things are what they are. I'd say your obligation, your choice, your prerogative to write the additional information that's needed for them, as long as we can get them in the forms together. Number 18. Y equals negative 6x minus 2 and 12x plus 2y equals negative 6. So this one is a slope of negative 6, y-intercept. The point is, when we look at this second equation, how does it change now in comparison? Is it the same? Is it different? Things like that. So is one solution an option? Yes, it is an option. We'll see if that ever shows up. If I subtract 12x from both sides and then divide everything by 2, you get y equals negative 6x minus 3. Notice this is negative 6x minus 3. Same. And then negative 2 and negative 3 are different. So same slope, different y-intercept. That means no solution. They're parallel. No solution, same slope, y-intercept, parallel. Again, my words to your paper if you'd like to add more information on that. So that's the conclusions we're making, right? So kind of nice, because I was stating earlier on, you have to keep solving. You have to keep solving. Here they're saying don't keep solving. Draw your conclusion off that. 4x plus 3y equals 27, and 4x minus 3y equals negative 27. I'm going to venture a guess and say this is not a special case because of how the y's are opposite signs, but the x's aren't. But we still need to compare the slopes and y-intercepts, and that's just me rewriting the equations. So subtract 4x from both sides and divide everything by 3. You get negative 4/3 x plus 9. This one, subtract 4x from both sides. But we divide by negative 3. Change of sign, positive 4/3 x plus 9. Now, they have the same y-intercept. That doesn't matter if the slopes are different. And these slopes are different. Mr. Robinson, one's 4/3, one's negative 4/3. Yeah, they're different. Different numbers. So they're not perpendicular either, not opposite reciprocals. But different slopes, regardless, doesn't matter what the y-intercept is. They're different slopes. This is one solution. Now, if they were both negative 4/3 or positive 4/3 together, something like that, well, then they'd be the same line. That'd be infinitely many solutions. This is a one solution case. By the way, I apologize sometimes when that thing's not writing. I need to change the tip on my stylus here. It seems to be bent and whatever. I just need to get new tips for them, but sometimes it's not making contact with the tablet. That's what's happening. It's not a software issue. It's actually a hardware issue. Number 20. Negative 7x plus 7y equals 1. If you get really good at this, you start to anticipate what answers are beforehand. I anticipate this to be a no solution case, for example. So here we ugly curly brace it. Add 7x to both sides. Divide everything by 7. You get 1x plus 1/7. Weird y-intercept, but whatever. And then here you subtract 2x from both sides. And then you divide everything by negative 2. That's 1x plus 9. 1x, same slope, different y-intercepts. Doesn't matter if it's a fraction, whatever, different y-intercepts. That would be a no solution case. Different y-intercepts, same slope. So I hope that my work is enough for you to understand that conclusion. Number 21. Negative 18x plus 6y equals 24. X minus y equals negative 2. Okay, top equation. Add 18x to both sides. Divide everything by 6. 18 divided by 6 is 3. 24 divided by 6 is 4. There's one equation. Here, I'm going to do this kind of faster. I'm going to add y to both sides, make it positive. So I can say y equals. And now the negative 2 is on that side. Let's add the 2 over. 3x plus 2. Boom. Does that make sense? So adding y, adding 2. Instead of 3x plus 2 equals y, y equals 3x plus 2. All right, 3x plus 2, 3x plus 4. Same slope, different y-intercepts. Different lines, but parallel. No solution. Love the conclusion. Love the conclusion. Number 22. 2x minus 2y, 3x minus 6y. Well, I'm anticipating one solution. And listen, guys, it's all about proportionality to me. If these don't grow by the same things. See, if this had 3x minus 3y, then we're talking about a special case. But this has minus 6y. So, a little different. Anyway, let's continue forward. Compare slopes and y-intercepts. That's their goal. Subtract 2x from both sides. Divide everything by negative 2. And I've already made mention of this plenty of times, and it's kind of too late for me to mention now, but I'm not showing the actions in between steps anymore. I'm going straight to them. Hopefully you're still able to follow along. I'm subtracting 3x from both sides now. I'll state what I'm doing. I just stated right there. Subtract 3x from both sides. Divide everything here by negative 6. Negative 3 over negative 6 is positive 1 over 2 when reduced, so 1/2 x. And 30 divided by negative 6 is negative 5. This is a slope of 1. This is a slope of 1/2, so it doesn't matter what the y-intercepts are. Different slopes means one solution. They'll just intersect once. What is that solution? They didn't ask us to find out. So that's all we're getting from that. All right, we actually only have 10 problems left here. We'll see what we can do. Obviously, word problems will come into the fray in a bit. But first, let's start with some error analysis. Ooh, I love this. I brought this up earlier, number 23. I'm seeing this for what it is. I brought this up earlier, now we get to talk about it. We have these two equations, and they graphed them. And I'm sure the graphs are right. If I look a little into it, 4x, I think these graphs are right. Right? They said the lines don't intersect, so the system is no solution. The issue is this isn't in their window range to see this thing by graphing. It's not that they don't intersect, it's that you just don't see the point of intersection. These graphs have different slopes. Therefore, eventually they will intersect. If outside the window range. Even if outside the window range. And the point I was making earlier was actually kind of opposite of what we're seeing here. The point I was making was if I gave a test or a quiz to my students, and I had pre-scaled axes, right? -10 to 10, things like that. And by the way, when we solve this, we probably have to use axes and talk about this, so I'm going to get them ready. Copy and paste. If I gave a problem to them, and I asked them to solve by graphing, I gave them axes and things like that. If they did have lines that intersected outside of the window range, boom and boom, like that, and you didn't see them, then you probably did something wrong, because I would not have them intersect outside the window range. I probably wouldn't even have them intersect at a fraction point. If you intersect at a fraction point, don't round it to the nearest whole number. If they intersect outside the window range and you don't see it, don't write no solution. And honestly, don't extrapolate. Don't go further out and figure out what it is. You probably did something wrong. You know what I mean? I want them to intersect inside the window range. Now, these ones might intersect within this window range. Their window range is a little smaller. Mine's a little bigger here. So let's see. They have -4x plus y equals 4 and 4x plus y equals 12. Now, if I did kind of standard form-esque stuff, here we'd talk about an x-intercept of, and listen, their graphs are right, but we have an x-intercept of -1 and a y-intercept of 4. So this graph has this right here, and then we can draw its line. So here we'd have little boomskis like that, and I'll extend it. This goes further up. The only problem with the next thing, and it would be the same problem even if we did it in slope-intercept form, is that this y-intercept looks to be 12 on this next one. So the one in green, the x-intercept is 3. Divide 12 by 4, you get 3. The y-intercept is 12, though, and that, even in slope-intercept form, that would be the case. So my only problem here is kind of bringing this about like 11, 12 like that, and drawing a line and just hoping for the best. But, I mean, these are going to intersect at an integer. If you think that we're going from, so they do intersect in the window range, which is nice. But if you think that from 12 to 3, we're going down 12 over 3, that's also down 4 over 1. What's down 4 from 12 as we go over 1? This point here, that's 1, 8. And that is the point of intersection here, 1, 8. So the point I wanted to make again was that they were outside of their window range. If the lines are not parallel, then they do intersect somewhere. If I want you to see where they intersect and I want you to solve by graphing, then I better have them intersect in the window range. Otherwise, if you don't see them do that, then you probably did something wrong. And the thing that's most often wrong is slope going the wrong direction, right? You graph something as a positive slope instead of a negative slope, things like that. So that's just the thing to be aware of. And this was a good point to make out of it. All right, number 24. These lines have the same slope, so the system has infinitely many solutions. Oh, contraire. And there's nothing I have to do with this afterward. We kind of just saw what happened here. Same infinitely many solutions only occurs when the lines are the same, which means the y-intercepts would also have to be the same. Because these y-intercepts are different, but with the same slope, these lines are parallel and therefore have no solution. So that's the correction. No solution, not infinitely many. So y equals 3x minus 8, y equals 3x minus 8, infinitely many. 3x minus 8, 3x minus 12, no solution. All right, number 25, modeling with mathematics. A small bag of trail mix contains 3 cups of dried fruit and 4 cups of almonds. A large bag contains 4.5 cups of dried fruit and 6 cups of almonds. Write and solve a system of linear equations to find the price of 1 cup of dried fruit and 1 cup of almonds. I guess the bag doesn't count as part of the charge. So the small bag is the one on the right that's $6. So if I'm going to let like x equal, let's see, cup of dried fruit, cup of almonds. Let's actually use F and A because those don't look like letters. Cost of 1 cup dried fruit. No, it's not writing. See, this thing's not registering anymore. I think I officially broke the tip here. Let's see. I'll keep trying. Cost of, wait, D, I want A. Cost of 1 cup almonds. Okay. When there are 3 cups of dried fruit and you multiply by the cost per cup, and 4 cups of almonds and multiply the cost per cup, and this is for a small bag, that'll equal $6 total. Dollars plus dollars equals dollars. And this other one has 4.5, all right, 4.5 cups of dried fruit plus 6 cups of almonds. So 6 cups times the cost per, and that's $9 right here. So this is our setup. They said write and solve a system of linear equations. So there it is written. This is one of those things where the decimal is not a favorite of mine. You may or may not know that dividing by 1.5, what's 6 divided by 1.5? Is that 4? 9 divided by 1.5 is 6, right? I'm going to kind of be clever with this. You can choose to do what you want. When I divide here by, I believe, negative 1.5, I think this thing really cleans up here. 4.5 divided by 1.5 is 3. So this will be negative 3, F. 6.5 divided by 1.5 is 4. 9. I said 6.5. 6 divided by 1.5 is 4. 9 divided by 1.5 is 6. And divided by negatives is negative 6. Now, why did I do all that? Well, cancel out the F's. But guess what? Gone go the A's, gone go the 6's. You get a 0 equals 0 case for that one. That means infinitely many solutions. Now, what we might have to do, see, they had in the lecture portion, they had a problem where they graphed it, and it was kind of anything in the first quadrant. So I'm not going to graph this one, but I suppose I could say infinitely many solutions where A and F are greater than 0. I assume the dried fruit and the almonds do cost some sort of money. This doesn't mean all real numbers, though, right? It doesn't mean, oh, I could do almonds. Wait, what was A? Almonds. Oh, almonds are $20 per cup and dried fruit is 50 cents per cup. No, it needs to fit on whatever line this is as a graph. And not that I am graphing it specifically, but those things will have to be the case. They're not going to be free. They're not going to be negative dollars, and anything that would be on this line would fit. But it is infinitely many solutions. It is quite interesting that we have these, and I don't know if we'll have no solution cases as well. But that is the final set. So word problems with infinitely many, kind of weird to me. They're kind of weird to me because we're not stating. If they said give me a solution that works, then we'll figure that out. But they're not asking for that. All right, in a canoe race, Team A is traveling let's leave this up here. Traveling 6 miles per hour and is 2 miles ahead of Team B. Team B is also traveling 6 miles per hour. The teams continue traveling at their current rates for the remainder of the race. Write a system of linear equations that represents the situation. Will Team B catch up to Team A? Explain. Well, if you read the information, whether or not you understood systems of equations, I think you might know what the answer is. So let's write these out like this. I'm going to use y and x. Y is distance traveled. X is number of hours, things like that. So 6 miles per hour for Team A and 2 miles ahead of Team B. So I could say this is like 6x plus 2. The 2 mile jump that it has, it's like a 2 mile head start of Team B, which is also going 6 miles per hour, but kind of at a plus 0, if you will, right? 6x plus 2 versus 6x plus 0. It says write a system. There it is. Will Team B catch up to Team A? Explain. We're basically asking for what value of x will they have the same y. So you'd set these equal to each other. When does 6x equal 6x plus 2? But you might already understand, subtracting 6x, you get 0. You get 0 equals 2. They'll never catch up. They're at the same speed. They're 2 miles behind. Team B will never catch up to Team A. So no solution. I also could have done a distance equals rate times time thing, but no solution. Team B will never catch up to Team A. Okay. There we go. All right. Number 27. A train travels from New York City to Washington, D.C., and then back to New York City. The table shows the number of tickets purchased for each leg of the trip. The cost per ticket is the same for each leg of the trip. Is there enough information to determine the cost of one coach ticket? Explain. Okay. Number of tickets purchased. So this isn't the cost here where we have to figure out cost. Let's let C equal cost per coach ticket, B cost per business class ticket. So C equal cost per coach ticket, I assume in dollars, and B cost per business class ticket in dollars. Okay. Pardon me. Okay. From Washington, D.C., we can do the equation 150C plus 80B equals 22860. The next one is 170C plus 100B equals 27280. Looking at these, I don't think 150 is the same amount of times larger than 80 as 170 is the same amount of times larger than 100. My basic point is if I got one of these by itself, like slope comparison, things like that, I think we're going to get one solution. I think they'd have different slopes. Now I'd have to work it out to tell it to you officially. Now I don't know if we're supposed to solve it. It says, is there enough information to determine the cost of one coach ticket? I think there is. I think this would have one solution. If you want to determine the one solution case, you could try and do the elimination thing and actually do it. You want to solve it? I suppose we can. If you compared slopes and y-intercepts, though, I'm going to do the slope y-intercept thing. I do know there's C and B here, but let's pretend like B was like your y, where we'd subtract 150C, and then we would divide everything by 80. So that would be B equals, and that's negative 15 over 8 plus something. I don't know if it's worth dividing. My only question right now is, do they have the same slope? I'm going to say no. 22860 divided by 80. Yeah, it's a weird number anyway. 285.75. This other one here, if I subtract 170C, and I divide everything by 100, you get negative 17 over 10. And that's the point. Oh, this is a C right here. And you get a different slope, right? They're reduced fractions, but you get a different slope. This is 272.80, like that. Different slopes means there's a point of intersection somewhere where you can solve for B and C and do that kind of stuff. But basically, different slopes means one solution. There is only one solution. Therefore, there is enough information to, what do they say? Determine the cost of one coach ticket. Now, did I actually solve it? No. Generally, I do in those situations, but and would I solve using like substitution or graphing or something? No. I was just trying to go along the lines of what we did in rewriting them in a slope-intercept form to say if the slopes are the same, then we can make a conclusion about them, and or if they're different, we can make a conclusion about them. That's how I played that one. Number 28, thought-provoking. I don't think we'll finish in the hour. Write a system of 3 linear equations in 2 variables so that any 2 of the equations have exactly one solution, but the entire system of equations has no solution. Any 2 of them have exactly one. So what we need is basically for them to have different slopes, but they can't intersect at the same place. So I could say, I'm really going to go in this format here, like y equals 2x plus 3. I need a different slope here, like y equals 3x, I guess, plus 2. Wherever these intersect, I need to make sure this other one intersects at a different place completely. To make sure it does, you can tell these have different y-intercepts. I need this one. Maybe this one can have the same y-intercept as one of them. Let's say 4x plus 2. That way, these two, I already know these two are going to intersect at 0, 2 together. This one will intersect at some other place with this, and then this will intersect at some other place with that, so with this as well. So listen, those are 3. That works out for me. As long as they have different slopes, they'll all intersect once somewhere. If these have the same y-intercept, they'll for sure intersect at that y-intercept. These will for sure not intersect at the y-intercept. Neither will these, and it'll be at a different spot. Boom. There we go. Number 29, reasoning. In a system of linear equations, one equation has a slope of 2, and the other equation has a slope of negative 1/3. How many solutions does the system have? Explain. Well, they have 1. Different slopes means they'll only intersect once. That is one solution. One solution. One point of intersection. That's it. They're not parallel. Not same slope. Not parallel, not same line. So there it is. It's actually kind of weird they throw that in the mix right there. That was something we kind of answered a long time ago. You know what I mean? Maybe we can finish in the hour. Number 30, how do you see it? Maybe not. The graph shows information about the last leg of a 4x200 meter relay for 3 relay teams. Team A's runner ran about 7.8 meters per second. Team B's runner ran about 7.8 meters per second. Parallel. And Team C's runner ran about 8.8 meters per second. So A is in blue, B is in red. They're running at the same rate, but A is ahead of them, I guess. C is running faster. Estimate the distance at which Team C's runner passed Team B's runner. Green passed red at maybe, it's about right there-ish. The time was 8, but probably halfway 25, I don't know, 37 meters, 38 meters, I don't know. I'll say part A at about 38 meters. 37.5 if I want to be, what I was thinking was, oh, it's exactly halfway between, and I don't know if that's true or not. Here, I'll say 38. I'll say, oh, it's exactly halfway between 25 and 50. So I wanted to say 37.5. I'll say 38. Part B. If the race was longer, could Team C's runner have passed Team A runner? Explain. Yeah, absolutely. So yes, because Team C's runner ran faster than Team A's. What they're saying is there a solution? Yes, there is. It doesn't matter if it's outside of the window range. Will it eventually catch up and intersect? Yes. Part C, if the race was longer, could Team B's runner have passed Team A's runner? Explain. No, not at those speeds. No, because they ran at the same rate. They run at the same rate, and Team B was already behind. That's the same as, there was a different question like that, right? What was it? Canoe race? I totally forget what the question was. But there was something else where it was one thing won't catch up to the other. The 6x plus 2 and the 6x. I forget what question that was completely now. All right, number 31. Yeah, I'm not going to finish this within the hour. Abstract reasoning. Consider the system of linear equations y equals ax plus 4 and y equals bx minus 2. Where a and b are real numbers, determine whether each statement is always, sometimes, or never true. Explain your reasoning. So part A says the system has infinitely many solutions. That could never be the case because these have different y-intercepts, therefore they could never be the same line. So part A, never. Different y-intercepts means different lines. Doesn't matter what A and B are. They'll never be infinitely many. System has no solution? Sometimes. If A and B are the same, then they'll have the same slope. So sometimes, if A equals B, then slope is same. Therefore, lines are parallel, and lines are parallel. Part C, when A is less than B, the system has one solution. That's always true. If A is different than B, they'll always have one solution. So always, the slopes are different, and they'll intersect at one point. Again, it doesn't have to be less than B. It could also be more than B. As long as it's not B, it'll be different. Excuse me. The last question is number 32. And my timestamps, even though we don't finish in the hour, the timestamps can stay under the hour. Making an argument. One admission to an ice skating rink costs X dollars, and renting a pair of ice skates costs Y dollars. Ice skating rink. Okay, the admission is X. renting a pair of ice skates is y. Your friend says she can determine the exact cost of one admission and one skate rental. Is your friend correct? Explain. So we already have what x and stuff are. So 3 admissions, 2 skate rentals is $38. And 15 admissions and 10 skate rentals is $190. Off the bat, I'm going to say no. I mean, you'll notice why when we do more of the problem. If I divide, and yes, I can divide. If I divide the bottom equation here by -5, I can eliminate x's. But gasp, what also happens? Y's are going to eliminate here as well. Is that -38? I think it's yeah, -38. And then these all eliminate. You get 0 equals 0, which is infinitely many solutions. What are we saying here? Well, you didn't change the pairing on how things work. You just did 5 times more admissions and skate rentals to get 5 times more of the cost. So we still don't know what the unique things are, right? If I did 1 admission and 1 skate rental, then it would be a uniquely different experience. So no, I have no way of determining for sure what 1 admission and 1 skate rental is. No, the system has infinitely many solutions. So any solution where now honestly though, admission's probably not free, so x is greater than 0, and same with the ice skate rental, and y is greater than 0 as possible. That would satisfy these equations. See, just to remind you, it's not any x and any y. It's not like you can just plug in anything. It's anything that makes this work. This could be $10 admission and $4 skate rentals. 3 times 10 is 30, plus 2 times 4 is 8. 30 plus 8 is 38, right? It could be that. Or it could be $6 admission for $18 and $4, $10 skate rentals, right? And that would be 38. So, and that would satisfy these ones as well at the same time. All right, guys, that'll do it for this one. This is Mr. Robinson. Thanks so much for watching. I'm glad that this still did things with one solution on them. It made us ask questions about them. I understand how word problems can be used in this light. It's a little weird that they didn't do them in the individual sections, but, you know, there it is. This wasn't superfluous information, but it was enriching information, and in a vacuum, you have to make sure that you understand how to do it outside of the vacuum as well. And maybe the quiz review will do that for us, which is coming up in the next video. So thank you so much, guys. Take care. I'm going to see you in the next one.